You know how a butterfly's wings are like a perfect mirror image of each other? Well, that simple, beautiful idea is called symmetry. And it's not just in nature, it's everywhere in math. It helps us see the hidden structure in graphs and the equations behind them. So today, we're going to pull back the curtain on this idea of balance. We'll start with what we can just see on a graph and then get into the cool algebra that proves it. No guesswork needed.
All right, here's the plan. We're going to start with the basic idea of a mirror image. Then, see how that looks on a graph. After that, we'll get into the algebraic tricks to prove it. And finally, we'll tie it all together with something really cool called even and odd functions.
So before we dive into any equations, let's just start with something we all get, right? That feeling of balance. You see when something is a perfect mirror image.
So just think for a second. When you look at a graph, what makes you go, huh, that's symmetrical?
It really all comes down to reflection. I mean, imagine you could literally print this thing out and fold it right down the middle along a line. If the two halves match up perfectly, boom, you found its symmetry.
Okay, let's get just a little bit formal for a second. The official math term is that something is symmetric if it's invariant. Now that's just a fancy word for unchanged. So if you can do something to it, like flip it or spin it, and it looks exactly the same afterward, well, it's symmetric.
Okay, now that we've got that main idea down, let's look at the three big types of symmetry you'll see on a graph.
So, first up, we've got y-axis symmetry. This is probably the one you're most familiar with, the one we all drew back in school. It's that classic mirror image right down the vertical y-axis.
So with y-axis symmetry, that vertical y-axis acts like a perfect mirror. For any point on the graph, say the point 1, 3 right here, its mirror image partner, negative 1, 3, has to be on the graph too. See how the y value is the same, but the x value just flips its sign? That's the key.
All right, so what happens if we take that same idea but just turn the mirror on its side? Well, that's going to give us x-axis symmetry. And here, the horizontal x-axis is our mirror. So a point like 1, 3 has to have a buddy at 1, negative 3. You'll notice the x value doesn't change, but this time, the y value flips its sign.
And now for the last one, origin symmetry. This one's a little different, you know? It's not about a reflection or a mirror, it's all about rotation.
A graph has origin symmetry if you can stick a pin in the center, the origin, and spin the whole thing 180 degrees, a complete half turn, and it lands right back where it started. It means if you've got a point like 1, negative 1, its partner on the total opposite side, negative 1, 1, also has to be on the graph. Both the x and the y coordinates flip their signs. But here's the thing, just looking at a graph can be tricky sometimes, right? So what's really, really cool is that we don't have to rely on our eyes at all. We can actually prove symmetry with algebra. This is where we go from just seeing it to really knowing it for sure.
And this table here, it connects everything perfectly. The visual rule we just talked about has a direct algebraic test. Just think about it. To test for that y-axis reflection, you just swap x with negative x in the equation. For the x-axis reflection, you swap y with negative y. And for that 180-degree spin around the origin, you swap both. If the equation somehow magically simplifies right back to what you started with, you've just proven it has that symmetry. It's that simple.
Okay, let's try this out on a classic, the equation for a circle. Now the key here is that both x and y are squared. So what happens when you plug in a negative value for either of them? Well, squaring it makes it positive again. It's like the negative sign just disappears. That's exactly why it passes the x-axis test, the y-axis test, and the origin test. The equation stays exactly the same every single time. How cool is that?
And when we look at the graph, yep, our algebra was right. A circle sitting at the origin is the perfect example of a shape that has all three types of symmetry. You could fold it, you can spin it, it always looks the same. The algebra didn't guess, it proved it.
Okay, so now we're ready to take this one step further and connect these ideas to a more formal concept in algebra. This is where we find this really beautiful hidden layer of structure in the world of functions.
It turns out that y-axis and origin symmetry are so important, especially when we're talking about functions, that mathematicians decided they needed special names to classify them.
And this is where we get those special names. A function with y-axis symmetry, we call that an even function. And that rule you see there, f of negative x equals f of x,
That's just a super compact way of saying, hey, plugging in a negative x gives you the exact same result as plugging in a positive x. And on the other side, a function with origin symmetry is an odd function. That's where plugging in a negative x flips the sign of the whole answer.
So, why even and odd? Where do those names come from? It's actually way simpler than you might think. The names come right from the exponents in basic functions. You know, if a function is built around an even exponent like x squared or x to the fourth, it's going to have that y-axis symmetry. So we call it an even function. And if it's built on an odd exponent like x cubed, it's got origin symmetry. It's an odd function.
And here is the perfect visual for that. On the left, you've got x squared, an even exponent, giving us that perfect mirror image across the y-axis. And on the right, a function driven by x cubed, an odd exponent, gives us that classic 180-degree rotational balance. The names literally describe the shapes you see.
All right, we've covered a lot of ground here, from simple mirror images to algebraic proofs and these special names for functions. So let's bring it all home and see what the big picture looks like.
So here's what it all comes down to. At its heart, symmetry is just a simple idea, a shape that doesn't change after a flip or a spin. We can spot it with our eyes, sure, but the real power is that we can prove it with those simple substitution tests in algebra. And this leads us to that powerful classification system. Y-axis symmetry means you have an even function, and origin symmetry means you have an odd function. And this isn't just about giving things fancy labels. It's like a secret weapon. It helps us understand and even predict how a graph will behave before we even start plotting points.
So we've looked at symmetry on these flat 2D graphs. But this core idea of invariance, of something staying the same even when you change something else, is honestly one of the most powerful ideas in all of science and math. You see it in physics, in chemistry, in art, in music. It's everywhere. So the question I want to leave you with is this. Now that you know what to look for, where else are you going to find it?